All right, thanks. Can everyone hear me? Okay. So I'm going to go through some basic ideas of how you get radio emission out of magnetospheres, and star-planet interaction is going to be an important case of that. But I want to do something which is more pedagogical and then start with what are the processes in a magnetosphere and why you should get radio emission from a magnetosphere and what are its properties. So my idea is to start from first principles. Of course, we could make an entire semester course on this. And so we don't have all of that time. So what I'll do is I'll try to simplify things such that the basic physical insight is clear, but maybe our derivations and all of those things are not very rigorous. Okay, so that's the idea I have. I did make slides for this talk, but then I saw this enormous, beautiful blackboard. And unfortunately, the university where I teach, we are slowly getting rid of our blackboards. And so I decided that I really want to enjoy this entire blackboard. So I'm going to just use the blackboard and chalk to talk about this. And there are some figures or animations if I have to show, we'll just do it later, or we'll do it in my lecture tomorrow. Okay. I just need one thing from you guys. So the people who are in the back row, can I trust in you to tell me if I'm writing too small and you cannot see? Perfect. Okay. All right. So let's start with discussing what a magnetosphere is. Okay. And my first job here is to bring all of you, raise all of you above in the atmosphere, because so far we have been talking about really the lower layers of the atmosphere, very close to the layers of the air we breathe right now, right? And so we have to go far, far above this layer to get into the magnetosphere and talk about all the interesting phenomena that happen in the magnetosphere. So I want you to take a guess at the size of the Earth's magnetosphere. So think about the magnetosphere as the boundary at which, if you cross that boundary, you're going to go into the solar wind. Okay, so take a guess at how far this boundary is. In any units of your choice, centimeters, Earth radii, choose a unit and just take a guess at how far away this is. 100 Earth radii. Okay, so that's any other guesses? Is there an intuition behind 100 Earth radii, or it's? Oh, okay, yeah. Any other guesses? 3? Did I hear 3 Earth radii? Okay. So the answer is very close to the geometric mean of the two. No, is it the It's about it's around 10 Earth radii. Is where you have like a bow shock, and then it's the solar wind beyond that. It changes, of course, right? It changes based on the conditions, but that's the scale of the object we're talking about. So the Earth radius is about 6,000 kilometers, right? So we're talking about something which is 60,000 kilometers in size. Okay, and to first order, the density of material is falling exponentially as you go away from the surface of the Earth. So you can imagine that we are talking about what is essentially, compared to the air we breathe, almost like a vacuum. So we are talking about an area where the density is extremely low, okay? And so we can immediately work out a few consequences of the density being extremely low. If the density is extremely low, then the recombination rate is extremely low. So any ultraviolet photon from the sun that ionizes the air has to do that working against recombinations, because the electrons will recombine and the atom becomes neutral again. But if the density is very low, then the electrons and ions cannot find each other, right? And so the recombination rate falls with density. And so what you have is essentially, after you get to a height of around 300 kilometers, which is what we call the ionosphere in the Earth, you essentially have a plasma. So you have electrons and ions separated. So you have a plasma. So we are going to be talking about mainly what happens in these plasmas. Okay. So that's the condition of the magnetosphere. Now, as the name also suggests, the Earth has a magnetic field. And so the magnetosphere obviously is named because it is dominated by the magnetic field. And what do we mean by that? We mean that the dynamics of this plasma, so everything is ionized. And so all the ionized species feel a Lorentz force from the magnetic field, and that completely dominates the dynamics of the plasma. So we can roughly work out how important the magnetic field is once you go to these layers on the Earth. So the best way to imagine that or to work that out to first principles is to realize that the currency in physics is energy, right? And so if you follow the energy, then you generally get to know what the important processes are. So let's look at what are the sources of energy in the magnetosphere of a planet. So let's take Earth or any exoplanet as an example. And so the first thing we have there is a magnetic field. And so the magnetic field has an energy density, okay? So, and the energy density of a magnetic field, I could write as P magnetic, let's say. And that is given by B squared by 8 pi. That's just the energy density in the magnetic field. So does anyone know what is the rough magnetic field of the Earth? So we could just take that as a value. 10 to the minus 3 Tesla. So it's very close. So yeah, so it's roughly a Gauss. It's 0.3 Gauss. So 10 to the 4 Gauss make a Tesla. So I'm very old school, so I'll use Gaussian units, which means we won't have mu's and epsilons to carry around everywhere. So that's the advantage. Okay, so this is roughly about 0.3. So it's of the order 10 to the minus 2, right? That will be roughly the order of this. And that's Earth per cubic centimeter. Okay, now that's the amount of energy that's there in the magnetic field per cubic centimeter. So let's see how much energy is there in the thermal energy in the plasma. So that is NKT, where N is the density, K Boltzmann constant, T is temperature. Okay, so the density in the highest density you can imagine in what you would call the magnetosphere starts at the ionosphere, because that's where everything gets ionized, around 300 kilometers. So there the density is around 10 to the 6. So again, everything is in Gaussian units. So 10 to the 6 per cubic centimeter is the density. Boltzmann constant is roughly 10 to the minus, I think 16. And T is, let's say, 10 to the 4 Kelvin. That's roughly the order of magnitude. Yeah, so this is of the order 10 to the minus 6 in the same unit, Earth per cubic centimeter. That's the thermal energy. So you can see that the plasma thermal energy is way lower than the magnetic energy. What about gravitational potential energy? Is gravity important when we want to understand the dynamics? Yeah, so gravity, of course, most of it would work on the ions because they are the heavier species. So that's going to be that's roughly the gravitational potential energy. Here I've assumed a hydrogen plasma. It's not hydrogen in case of the Earth. So you would not have proton mass. You would multiply that by the atomic number. I don't know by heart what the gravitational constant is. So I'll give you the rough numbers. So here I've been conservative and I've said, let me take a planet of 10 Earth masses, okay? And again, a density of 10 to the 6. And it goes inversely with the radius. I hope everyone knows the notation. This means the radius of the Earth. This means the mass of the Earth. Okay. So not important. Okay. So we can simply forget that gravity exists when we do our calculations in the magnetosphere because it's just energetically not important. There's one other thing, which is if the Earth is spinning and charged particles are tied to the magnetic field because of the Lorentz force. And that means that because the Earth is spinning, its field is spinning with it, and it makes all the charges also spin. So the charges have to co-rotate at the same angular rate as the Earth. And that has a consequence, which is that the further out you are in radius, the faster you have to move. Okay? And so that itself, you could call it a centrifugal potential if you want to write it in terms of energy. it works out to be the same as, so that's basically kinetic, it's a form of kinetic energy, right? So that's half mass. So this is the energy density. So mass of the proton times the n is the density, the volume density. And then v square. So v is the velocity. So that's just going to be omega times r. Right? And that energy exists just in the form of kinetic energy. And that works out to be, I'm just going to write it in terms of period. So that's small, but it's going up with radius as r square. So can become important at large radii. Okay, because notice that the gravitational potential energy is just dropping with radius. Thermal energy depends on temperature, so it's not going to change with radius. Centrifugal, the kinetic energy in rotation actually is going to increase with radius because it is co-rotating. Okay, it's not in Keplerian rotation. Because of, remember, gravity is not important, so it's not in Keplerian rotation, it's in co-rotation because the magnetic field is forcing the plasma to co-rotate. Okay. Now, the magnetic field is to first approximation a dipole. And that's a very good approximation for most planets. And we expect it to be the same for exoplanets also. And an essential property of a dipole is that the magnetic field, as a function of radial distance r, is going to be proportional to r to the -3. So the magnetic fields fall very rapidly with radial distance, which means that the magnetic energy density is going to plummet as r to the -6. So at some point, this is going to win, right? Just the kinetic energy of motion of plasma is going to win, and that's inevitable in a magnetosphere. Okay, so that's, yeah, question. Oh, it comes from omega. Yeah. Omega is 2 pi by p. Right? Yeah. If it is for the Earth, this value would be 1. It would be 1 day. Yeah. Exactly. Yeah. So here, if I put 10 Earth radius, yeah. So it's going as r square. So it's increasing very rapidly. We can't because this is increasing with radius, right? It's not decreasing, it's increasing with radius. Will also vary. You're right. Yeah. So I'll come to that. So right now, that's why I've been careful to put tildes everywhere here, right? I mean, these are just order of magnitude, rough estimates. Yeah. So number density, of course, will also change, and that makes a difference. Yeah. 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 That is true, and that is an essential thing. That is essential for radio emissions. And so you are absolutely right. At some point, the magnetic field doesn't have the energy to force the plasma to co-rotate, and very interesting things happen. And so that's where we are going basically. Yeah. Okay, so those are the conditions in a magnetosphere. Okay, so based on this, we can already from first principles figure out a few things. One is that if you have a magnetosphere around a planet, it's going to be close to the planet. It's going to be a dipole, okay? Because the magnetic field completely dominates. It doesn't care what the plasma is doing. It can bend the plasma to its will, basically, right? So close to the planet, you're going to have this kind of a dipole structure. And I'm drawing the magnetic field here. It's going to look like that close to the planet. But as you go further away from the planet, as you mentioned, it's unclear what happens because at some point the plasma is going to win out. and the field will not be able to keep the plasma in co-rotation. Okay. So far away from the planet, what happens depends on a few things. And all of these are seen in different types of astrophysical objects. Okay. So there is one ultimate limit which cannot be crossed, which is that you cannot co-rotate faster than the speed of light. Okay. So at some point, at some radial distance, if the co-rotation speed becomes equal to the speed of light, that's called the light cylinder. And this is the effect which is seen in a pulsar, because a pulsar is very fast spinning. At some distance, the co-rotation speed equals the speed of light, and then the field cannot keep the plasma in co-rotation. Okay. We don't have to worry about that because planets don't have such fast spins. So we usually never reach the light cylinder of a planet. Other effects take over before that happens. Okay. The other thing, so if you come down from pulsars in kind of energy of objects, the thing that happens in stars is that stars have a really hot plasma and a really dense plasma compared to in their coronae. Okay. So, and that plasma is thermally expanding. So in case of the sun, it thermally expands, and we call that the solar wind. So at some point, the ramp pressure of the wind, so half density V square, exceeds the magnetic pressure. It has to happen because the magnetic pressure is falling extremely rapidly with radius. And then the field lines open up. The plasma forces open the field lines. So if this were the sun, then at some point, what is going to happen is that the field line is so weak at this radial distance that the expanding plasma forces it open, and then you get open field lines, like so. And then the plasma is free to flow along the open field lines, and we call that the solar wind. Okay, so that's what's happening in a star. Now let's see what happens in a, yeah, question. In case of the star, it's actually the ramp pressure, the ramp pressure that wins. Because what happens in case of the sun is you have a 1,000,000-degree plasma, and the base density of the plasma is about 10 to the 9, 10 to the 10 per cubic centimeter. And so what happens is that plasma adiabatically expands. And so eventually you wouldn't call it thermal pressure because it crosses the sound speed, and then it's just like a bulk flow. So then you just call it the ramp pressure. So it'll be half rho V square, where V is the bulk flow speed, instead of the thermal speed of the part. Yeah. So that's what happens in the sun. But in a planet, the planet doesn't have that kind of energy in its plasma to force open the field lines. So what happens in a planet is that to large distance, the plasma actually co-rotates. Okay. But at some point, like you just mentioned, the magnetic field has to, as the plasma moves outwards radially, the field has to constantly keep accelerating the plasma, and at some point it cannot. It can't provide the energy, and so it gives up right at that point. And that is essentially what happens in Jupiter. In Jupiter, we have that scenario. In the Earth, this would happen. This would happen at some radius, but the Earth doesn't get a chance to reach that radius because there is an external forcing on top of the magnetosphere of the Earth. Okay. And that external forcing is by the solar wind plasma. Okay, so what happens is the Earth, so let's suppose this is the night side for sake of argument, and this is day side. Now I'm imagining this is the Earth. It was the pulsar, it became the sun, so now this is the Earth. Okay, so this is the night side. You have the solar wind plasma that is coming in and falling onto the magnetosphere of the Earth. And so there is an external pressure in the solar wind which is impinging on the pressure of the magnetic field. Okay, so this is also a pressure, right? It has the same units as pressure, Earth per cubic centimeter. So this is the pressure that is applied by the magnetic field to stay, to have this dipole form. But there's an external pressure that is trying to compress the magnetic field from the outside. And because the field of the Earth is falling so quickly, at some radial distance, it cannot sustain the pressure from the solar wind. Okay? And so that is called the magnetoforce, and that is the 10 Earth radii, which I mentioned. Okay, so that's where the size of the magnetosphere comes from. So the Earth never gets to reach the breakdown of co-rotation. Jupiter does because it's further out, it has a stronger field. The solar wind pressure is weaker because it's at 5 AU instead of 1 AU. And so at Jupiter, that happens. So all of these effects are important for radio emission. And I'll, of course, explain why these effects are important. But I just wanted to first give you a general sense of what a magnetosphere is, what its structure is going to be like, and what are the important physical effects one needs to consider when we talk about the magnetosphere. And the important physical effects, of course, comes, you have to follow the energy, because that usually gives you the answer in physics of what is really important. Question. Sure. So what we could do for the solar wind is we could say, so let's make a list of pressures on two sides. On the Earth side, the pressure is simply the magnetic pressure, right? So that's going to go as d square by 8 pi. And that is, let's say, the surface field. Yeah, so the magnetic field is falling as r to the minus 3, and at the surface it's b naught. And so it's going to fall with radius as r to the minus 6. On the side of the solar wind, there are three possible pressure terms. Only one of them will dominate, as you'll see. One is simply the thermal pressure because of thermal motions of particles, right? So that is going to be NKT. That's just thermal pressure. Then there is ram pressure because there is bulk flow of the wind. So that is half rho v square. Rho is the density. So that's going to be that's how rho v square. And the solar wind also is magnetized. So it has its own magnetic pressure. That's going to be that. So you balance these two and solve for R, then that's how you get the size of 10 Earth radius, basically. Yeah. Does that answer the question? That's right. So the temperature we should use should be the temperature of the wind. In the corona, the temperature is about 10 to the 6 Kelvin. By the time it reaches the Earth, it's more like few times 10 to the 5 Kelvin would be the temperature of the wind. So this is around 10 to the 5 Kelvin. Solar wind density is 1 particle per cubic centimeter at 1 AU. So that's 1. The magnetic field of the interplanetary, hang on. Why don't we just do this calculation? Because I do have it done in my notes. Yeah, so the speed of the wind, solar wind at the location of the Earth is 500 kilometers per second, roughly. Again, these are all rough values. It changes, of course. And the solar wind magnetic field at the location of the Earth is about 10 to the minus 4 Gauss. That's the field of the solar wind. So you put all of that together, then it's the usually the interplanetary magnetic field that in the end dominates in case of the solar wind, and that comes to about that comes to about 10 to the minus 10 Earths per cubic centimeter. And so you balance that with this, and then you get R. Okay, so that's what. Yeah. Yeah. Oh yes, yes, it does matter. Yeah, it does matter. So now we are getting into the detail of how the wind interacts. And it actually, in case of the Earth, it interacts with reconnection. And so how the Earth's field and the solar wind magnetic field reconnects does have an impact on what happens at that boundary. No, this is all at the order of magnitude physics kind of level. Yeah. Okay. So I want to now get to the radio emission part. Okay, so we now know roughly what will happen in a magnetosphere. I hope you all have some intuition for what happens in a magnetosphere. So just to recap, forget gravity, right? Gravity is not important. It's all plasma, and the plasma is tied to the magnetic field till the field cannot anymore. Okay, those are the important parts. Okay, and so now the question comes to, okay, how do you remotely observe the magnetosphere and figure out what is happening? And a fantastic tool we have is radio emissions from this magnetosphere. And so I need to then talk about what happens with why do you get radio emission from a magnetosphere and what are its properties? Okay, and once we do that, we are going to get back to this picture we have. And then we are going to flesh out this in a little more detail. So I'll take the example of Jupiter, let's say, and actually work out at what point core rotation will fail, how much energy should be released because the core rotation is failing, how much of that will come out as radio waves. Okay, but before that, I need to first tell you why you even get radio emission from a magnetosphere. And for that, we could start with the simplest situation, which is you simply take an electron and you put it in a magnetic. Okay. And so you could solve for the dynamics of an electron. So let's say you take a uniform field along the z-axis. And then you can ask yourself, what are the dynamics of an electron if I put it in this field? And I think you would all have solved this already. And so you could basically write that's basically the Lorentz force law. Well, I'm using Gaussian system, so there's V by C here. There is no electric field, there's just a background magnetic field, so you just have the magnetic force. And the solution to this, I think most of you would have solved it, is Vz will be constant. But the electron will perform circular motion in the xy plane. So you're going to have V phi, which is going to be some radius, which is called the Larmor radius, times the cyclotron frequency. And that cyclotron frequency yeah, I'm assuming you've all seen this before, right? So yeah. Now there is a fantastic property of cyclotron motion, which will become very important very soon. And so let's notice that. What is amazing about cyclotron motion is this angular frequency depends on the magnetic field. That is not surprising. It depends on the mass. That is not surprising. What is interesting is what it does not depend on. And what is interesting is that it does not depend on the energy of the electron. Okay, and that is interesting. It does not depend on the amount of energy. What changes with energy is the perpendicular velocity perpendicular to the field. And what changes with energy is just the radius of gyrations. The Larmor radius is the only thing that changes. That means that unlike planets going around the sun, electrons going around the magnetic field all go around with exactly the same rate. Okay. If an electron is very energetic, it just goes on a bigger circle, but they all go at the same rate. And this has a fantastic consequence for radio emission because all of them going at the same rate creates the possibility of resonance. And that is what can create extremely bright radio emission. And I'll show you how that happens. Okay. Okay, so we have an electron. It's just going in a uniform magnetic field. Of course, our magnetosphere is not a uniform magnetic field. It's curved, as you can see. And not only curved, its strength is varying, right? So it's not. So we have to make this a little more complicated. And so the first thing we notice is, suppose I put an electron somewhere here, right? And it's gyrating over there. But let's say it has a parallel velocity, this. So it's going to start going along the field line. And it's going to follow the field line and go towards the pole. And here you have the first problem, which is the electron, the center of gyration, which is called the guiding center. This has to go on a curved trajectory. And that means that it will experience a centrifugal force. And the only way it can stay on the trajectory is if there is a balancing force acting on it. And the only thing they're providing a force is the magnetic field. And the magnetic force is always perpendicular to the velocity. Okay. And that means that the only way the electron can follow the curved trajectory is if it also has a velocity component outside the plane of the board. Because then the cross of that velocity component and the magnetic field will provide the centrifugal force, the balance to the centrifugal force. And that's called curvature drift. So what would happen is the electron is gyrating, it is going along the field line, but it's also gyrating in azimuth. So if you imagine the Earth in front of me, the North Pole on top, the South Pole below, you have this electron which is going towards the pole, but it's also moving in azimuth. So it's moving in longitude, okay? And of course, ions will move in the other direction. So that's the first consequence. For the radio emission, that consequence is not so important. What is really important is the fact that the electron is going into a region where the field strength is increasing. Okay, so the field strength along a line, along a magnetic field line, as you go towards the pole, you can see that the lines are getting crowded. And the line is, it's not a real thing. It is just a way for us to imagine the magnetic field. And the magnetic field strength is given by the density of those lines. Okay, so towards the pole, the field strength is increasing. And so that has important consequences also for what happens to the electron. So let's see what's happening there. So if you go near the pole, then you see magnetic field lines. That's what the electron will see, right? As it's going towards the pole, the field lines are all converging from its sides, okay? So that's what the electron sees. Now you have, this is the z-axis, let's say. There's the z-axis and the field lines are converging. So now you have a magnetic field which also has a component in the transverse direction, okay? So let's assume cylindrical coordinates. So you have z, which is going towards the pole. Imagine that the electron is going towards the pole, okay? And then there are field lines which are converging from all directions. So you have a rho component in cylindrical coordinates of the magnetic field. And you can solve that because you know that the field has to be divergence free, because there are no, the field has to follow this because there are no magnetic charges. So this has to be true. And so you basically, if you write the field in cylindrical coordinates, where z-axis is towards the pole and rho is the transverse coordinate, rho and phi, sorry. Then you basically, you could write out the divergence condition. And then I need to check if that must be 0. Yeah. So locally, so let's think locally. Locally, let's say we take some value for this, epsilon. Okay, so that is the gradient. That's how fast the field is increasing in strength as you go towards the magnetic pole. And that, let's say I call epsilon. And then that's a pretty easy equation to solve. Then you get B of rho. It makes sense that it's negative, right? Because the field lines are going towards the center in the rho direction. Okay. So we have to reconsider the motion of the electron now because we don't have that uniform field anymore. So let's see what happens to the motion of the electron in this case. So you again write out the Lorentz force law. But now that Lorentz force law will have a z component. Why does it have a z component? Because the force is V cross B, and B now has a rho component. Yeah. So now the Lorentz force will have a z component. And that is just to expand, you just have to expand the cross there. So I've done that. And so you get a z component of the force. So I've just used that here, basically. Okay, so now the electron also is going to get accelerated in the z component. Okay, so before what we had was the z velocity was constant, but now there is an acceleration. And that force is called the mirror force. And you'll see why it's called the mirror force very soon. So I could write this out basically. So I'm going to try to write this basically out in terms of the Lorentz force, in terms of the perpendicular kinetic energy of the electron. And you'll see why I would write it that way very soon. So that can be written, and I'm just going to move quick. You could check the algebra later. Okay, so now there is a mirror force, which is a force along the z component, and that force depends on how quickly the magnetic field is decay or is increasing in the z direction, and the perpendicular momentum, perpendicular energy of the electron. Okay, so mv square is basically the energy of the electron because of its gyration, the kinetic energy of the electron because of its gyration. Now that quantity mv square by 2 divided by the magnetic field, this is called the magnetic moment of the electron. Okay, so this is mu, which is the magnetic moment. That means that the electron is going to be pushed back because there is a force acting in the negative z direction on the electron. So as the electron goes towards the magnetic pole, it's going to be pushed back by this mirror force. And so what's going to happen is at some point, some electrons are not going to make it till the surface of the planet. They're just going to get pushed back by this mirror force. And that mirror force is simply a consequence of converging field lines, right? And so those electrons are going to return back, cross the equator, all the while they are gyrating, of course. They cannot help but not to gyrate. And they're going to go to the other pole, but face the same situation at the other pole. Because even there, the field lines are converging. So they get another mirror force. They experience the mirror force and they go back. So these are called trapped electrons. They're trapped because they keep bouncing between the two poles. Okay, and this is what is called a magnetic trap. The same concept is also used in a fusion plasma to confine plasma in a place. It's a fantastic way to confine plasma. All you have to do is to make the magnetic field increase in 2 directions, and then the electrons can never leave because of the mirror force. So exactly the same thing also happens in case of planetary magnetospheres. You basically have traps in magnetospheres. The direction of gyration. The direction of gyration would only depend on the V cross B force. So when it comes back, it only depends on the direction of the magnetic field. So direction of gyration is determined by the charge, the sign of the charge, and the direction of the magnetic field. Yeah. So what's the best way to think about what happens to these electrons? Is the easiest way in this scenario is to write out some invariants of motion. The first invariant of motion is the kinetic energy of the electron. Why? Because the magnetic field cannot do any work on the electrons because the force is always perpendicular to the field, right? And so we have one invariant, which is the kinetic energy. So we could write d by dt of what I mean by this is just the perpendicular kinetic energy. And this is the kinetic energy parallel to the magnetic field. V parallel is Vz over there. Vz, sorry, because we have taken the magnetic field to be along the z axis. So I'll post this if you want, just to save time. I need to not do all the algebra here, but you could combine this, and then show that the quantity, if, so this is true regardless, right? There is no mirror here, there's nothing. This is true regardless of what the field is like. But now we have a mirror force because of the field. So you could combine these two, and then you could show that the moment is always conserved. The magnetic moment has to be conserved of the electron. That's called an adiabatic invariant. Why is it called adiabatic? Because we have done some kind of a perturbative exercise by assuming the field to have like a slope locally, right? And so that's why it's called an adiabatic invariant. So nu, if you remember, nu is the perpendicular kinetic energy divided by the field strength. Okay, so let's imagine what happens. So suppose you have an electron that starts at the origin, at the equator. It has some component. Question? No. Are there any questions so far? Yes. That is true. That is true. I think the mistake I made here, which you did catch, so that's very nice, is that the V phi here, this must have a negative sign to get the correct force. Yeah, so you're right. I did make a sign error. This needs to have a negative sign. You could verify that. So you have a field going in the Z direction, let's say. If V phi is positive, then V cross B is going to go outward, but you need a force that goes inward for gyrations to exist. So that's why you need a negative sign there. Yeah, so thanks for catching that, you're right. Okay, so let's assume what happens. So you're an electron, you're starting at the equator, the magnetic equator. You have some parallel velocity or some perpendicular velocity. Okay, some velocity parallel to the field, some velocity of gyration perpendicular to the field. Okay, and we could specify that as the pitch angle of the electron. Okay, so we could say that your velocity component, we can call that the pitch angle, where this is the magnetic field. And then we could basically say that your perpendicular velocity, which is V phi over there, because if the field is along the z-axis, the perpendicular velocity is V phi. So we could call that okay, so you have these velocities, you have started, so you're gyrating, and you have a parallel velocity, so that brings you along the field line and you go towards the pole. What happens? You have to conserve energy. So V naught cannot change, because half m V naught square is the kinetic energy of the electron. That can't change. B is changing, but you have to conserve this ratio. The only way when B increases for you to conserve the ratio is to increase K perpendicular. So the perpendicular velocity should increase. But some of their squares must remain constant. So the parallel velocity should decrease, which makes sense. That's the mirror force you're experiencing. The parallel velocity decreases, and what will be your fate depends on your starting pitch angle. Why? Because if your starting pitch angle is very small, by the time your parallel velocity goes to 0, you would have reached the surface of the planet, right? And so you're not in the magnetosphere anymore at that point. So in case of the Earth, this happens in the ionosphere, where the collision rate is high enough that you're going to collide with the gas there, and you're not coming back to perform the bounce motion. Okay, but if your pitch angle is large enough, then you're going to stop before you're going to hit the atmosphere of the planet, and you're going to return, and you'll just symmetrically return to the same angle, the same polar angle on the other side. Okay, so if I place electrons in the magnetosphere, unavoidably, I'm going to create an anisotropic velocity distribution. So let's say this is V parallel, V perpendicular, okay? So the velocity distribution is three-dimensional. So imagine the third dimension is coming in and out of the plane of the pore. But for us, all in the third dimension, you just have gyrations. So all that matters is the perpendicular velocity for us. You are going to create a cone, right, of some of pitch angles where all the electrons which are inside this cone will be lost in the atmosphere. They are never going to return to the magnetosphere. And all the electrons outside this cone will return to the magnetosphere because of the mirror force. Okay, so all the electrons inside this cone have very large parallel velocities. So they will hit the atmosphere before they get reflected back by the mirror force. And that's called a loss cone. It's because it's a loss of electrons in the cone. And so the other result we can immediately state is that in a magnetosphere, the electrons don't have an isotropic distribution. Okay. Of course, there is a fundamental assumption here, which is that the collisions are not important, okay? Because the gas is so rarefied, it's not a collisional gas. Because the moment it's a collisional gas, you cannot avoid the Maxwellian distribution. The collisions will just establish a Maxwell-Boltzmann distribution for the velocities. But because it's not a collisional gas, you're going to get this kind of a loss cone distribution. The loss cone distribution is very interesting because there is free energy available here, which can be radiated as electromagnetic waves. Okay, so I'll explain how that happens, but I can give you a basic intuition of why you would get electromagnetic waves. In a loss cone distribution, you have what is called a population inversion, which is you have more momenta, you have more electrons at higher perpendicular momenta than lower perpendicular momenta. So because you have a deficit of electrons inside this cone, along the boundary of the cone, you have a scenario where you have a lot of electrons at higher perpendicular momentum than lower perpendicular momentum. So whenever there is a wave particle resonance, there will be more electrons that give energy to the wave than take energy from the wave. And that creates exponential amplification of radiation. So this is a classical analog of what you would call stimulated emission of radiation. It's a purely classical effect. So it's called induced emission because it's a purely classical effect. But the idea is very similar. Whenever you have an inversion of population, you could create an exponential amplification of waves. And that's what makes the radio emission detectable from these objects, because there is exponential amplification of waves at the resonance frequency, which is the cyclotron frequency, which we just saw. Yeah. So are there any questions? Because I'll now show why there is exponential amplification. But any questions so far? Okay. Is everyone able to follow? More or less? Okay. Okay. Why is there exponential amplification of waves? Well, that's because there's a wave particle resonance at the cyclotron frequency. Okay. So imagine that you have an electron which is gyrating at the cyclotron frequency. So let's make it simple. I'm going to assume that the electron is just gyrating in a plane. There is no z component of velocity. So I can write its velocities as okay. So that velocity gives you an acceleration. Now that accelerating electron must radiate because it's accelerating. So let's look at what the radiated fields will look like. So the radiated field, if you look at the radiated fields, the electric field will be polarized. That's the polarization of the electric field of the radiated charges. So n is the direction of radiation, is the unit vector, and a is the direction of acceleration. Okay. So I have an electron which is now gyrating. Now it's going to radiate in all directions. And let's simply, for the sake of simplicity, right, just consider the fields along the z-axis. So you're looking at an electron which is gyrating in the xy plane, and you're somewhere on the z-axis. Okay, so the fields you're going to see are going to be polarized again in the xy direction because of this, and you're going to see a field which has an electric. You'll see an electromagnetic wave that that um, that has X and Y components that look like this. So the X component behaves like a cosine, Y components behave like a sine. So what you have is circular polarization, right? So you have an electric field which, as a function of time, is rotating in the XY plane. So that's a circularly polarized wave because the electric field, as a function of time, rotates perpendicular to the direction in which it's propagating. Now, here's the interesting part. Now, let's say that you place another electron somewhere on the z-axis. The question is, what happens to that electron? Okay, so one of the electrons has radiated a circularly polarized wave because it is gyrating. Now, let's say I place another electron, which is also gyrating because they cannot help but gyrate. They're in a magnetic field. What happens when they experience this field? Now, this field is going to apply a force on them. Okay, and that force might do work on those electrons. Okay, so let's see what the force is going to be on those electrons and what the work will, which is done on those electrons. And now I'm going to assume that the second electron has a slightly different cyclotron frequency. I can ask, how is that possible? Because that should only depend on the magnetic field. And here is where you need to invoke a relativistic effect. So even though the cyclotron frequency only depends on the magnetic field, if the electrons are accelerate, if they have high energy, then their effective mass is going to be equal to gamma times m. So their gyration frequency will be slightly different if they are high energy electrons, because their effective mass has a factor of gamma in front. So highly energetic electrons will have a lower cyclotron frequency than lower energy electrons because they feel heavier. They're harder to accelerate, they feel heavier. Okay. So let's say these electrons have a slightly different cyclotron frequency. I'm just going to call it, let's use omega prime. Yeah, let's use omega prime. So let's say the second electron okay. So of course, this field is going to change the dynamics of the electron, but let's say this electric field is weak. So to first order the work done by this field, I finished the blackboard. That was my goal. So I've achieved it early enough, so that's good. So the rate of work done by the field on the electron is force dot velocity. That's the rate at which the field will do work on the electron. So you have the X and Y components of the force, which is going to be proportional to E basically. The force on the electron because of the electric field is Q times the electric field. And that's the velocity, right? So if I dot these two, then I'm going to get an expression which basically looks like sine A cos B minus cos A sine B, right? So I'm going to get an expression that will be so that's the rate at which the field will do work on the electron. Let's see what this implies. Suppose the second electron had a completely different Lorentz frequency of gyration compared to the first. This will average to 0. So if you have electrons who have wildly different gyration frequencies, then the average work done on them over many, many cycles is going to be zero. But remember that in case of cyclotron motion, except this factor of gamma, almost all electrons are gyrating at roughly the same frequency. So they are all in resonance. So because of that, there will be net work done by the wave on the electron. That work can be positive or negative, of course. The electron could do work on the wave as well. And so let's see which direction that work goes in. If the second electron is, let's say, has a lower cyclotron frequency, that will happen if its Lorentz factor is larger. So it's a more energetic electron and it has a lower cyclotron frequency. Okay, so in that case, because omega b is lower, the work done is negative. Okay, so that means that the electron does work on the wave. And as a consequence of that, its Lorentz factor will decrease and its cyclotron frequency increases. So what's the effect of it? The effect of it is that all electrons will be brought into perfect resonance just because of mutual interaction of their radiation on the other electrons. Okay, faster electrons will be slowed down, slower electrons will be sped up. That's what is going to happen. And so now you're going to have all the electrons gyrating in unison. So this is like a phase locking of the electrons. And because of that, their radiation is going to add in phase. Their electric fields will add in phase. It's not their powers that add, it's their electric fields that add. And Poynting flux is proportional to the square of the field. So if you have n electrons, you get a boost of n square when you add their electric fields. Whereas if they were all incoherent, then you would just get n times the power radiated by one electron. But because they are all coherent, the power radiated will be n square. Okay, so this is just to give you an intuition for what's happening in this amplification of radiation. Of course, for all of this to work, you need almost monoenergetic electrons, right? Otherwise, this doesn't work. They have to be close to monoenergetic. But this kind of exponential amplification also works in the general case. It is just that the derivation is much more demanding algebraically. But this gives the essential, hopefully this gives you an essential insight into why you get extremely bright radiation. It is because of that resonant property and the interaction of electromagnetic waves and the electrons at that resonance. Now, close to the resonance, you can receive energy from the wave, you can give energy to the wave. So waves and particles can do work on each other close to the resonance. And which wins will determine if the electromagnetic wave is exponentially damped or it is exponentially amplified. And which wins depends on whether you have more electrons at higher perpendicular momenta or less, or it depends on that balance between the electrons. And that's why when you have a loss cone distribution, it's called an unstable distribution. It's highly unstable because this gradient in perpendicular momentum, this inversion of population, means that there are more electrons that give energy to the wave than the other way around. So you get an exponential amplification of the wave, and that is called a cyclotron maser. Maser being even though it's not a quantum mechanical effect, it is a classical analog of the quantum mechanical stimulated emission effect, right? Because what you're seeing here is basically induced emission, which is a classical analog. So that's why it's called a maser. So that's called cyclotron maser emission. And that is the kind of radiation which you expect, the extremely bright radiation you expect to see from magnetospheres. And that radiation has some fantastic properties. One of the property is that radiation happens very close to the cyclotron frequency. Okay, so other than the Zeeman effect, this is the only method we have to remotely measure the magnetic field of anything in astrophysics. Okay, it's not model dependent. It's a direct measurement of the magnetic field because you're measuring the cyclotron frequency where the electrons are gyrating. Okay, and by measuring the cyclotron frequency, you've measured the magnetic field at that location. So this is one of two ways available in astrophysics to measure magnetic fields. The other being the Zeeman effect. That's a purely quantum mechanical effect. This is a purely classical effect. And because this question, I'll finish. Okay. And because this happens in magnetospheres of planets, and because we can't measure Zeeman splitting of lines from the atmospheres of these planets, detecting their cyclotron radiation is probably going to be the only way we have to measure the magnetic fields of planets, or to even say if they have magnetic fields. Okay. And this is quite a reliable statement because in the solar system, any planet which has a magnetic field radiates cyclotron maser emission. Okay, so we see it from the Earth. We don't see it from Mars and Venus. They don't have, or Mercury. They don't have magnetic fields. We see it from Jupiter. We see it from Saturn. We see it from Uranus. We see it from Neptune. Okay, because they all have magnetic fields, and we can look at their emission and figure out what their magnetic field strength is. Question. Yes. Yeah. Yeah, they'll be more or less independent because they all have different resonance frequencies. So this the maser has it is exponential amplification, and it has a growth rate which you can calculate as an integral over the momentum distribution here. So you can figure out which electrons here are resonant in any given location in the magnetosphere. And then along the resonance circle here, you can calculate the growth rate. It's an integral over the momentum distribution. That growth rate is extremely large. So for all practical cases of interest, that growth rate is usually 1% of the cyclotron frequency. Okay, so the growth rate is the rate at which you are getting e-folding in the amplification. So it's just 1%. So the Earth's magnetic field is about 1 Gauss. Its cyclotron frequency is about somewhere around a megahertz. 0.3 Gauss is a megahertz cyclotron frequency. So there the growth rate would be 10 to the is 1% of that. So it will be 10 to the minus 4. That means that every 0.1 millisecond, you get an e-folding of the wave. So this is a very local phenomena because the growth is so fast of the maser. What happens is, well, the growth cannot go on indefinitely, of course. So what happens is the electrons get a back reaction to the radiation, and eventually they diffuse into the loss cone because of the back reaction. And then the masing stops, right? But all of that happens in, let's say, 10, 20 e-foldings from the thermal level of radiation. And so everything is over in like 10 milliseconds. So what you get is, if we had the infinite angular resolution, it would look like a Christmas tree with like little maser sites maser instabilities going off, and we see the aggregate emission of that. Yeah. So you're right. So you're having that maser happening all over the polar regions because that's where the loss cone distribution is forming. And you get a lot of different masing sites. And then depending on where you are, the emission frequency changes. Because if you're further out in the magnetosphere, then the emission frequency is lower because the magnetic field there is lower. But the emission frequency can never exceed the surface magnetic field because you can't get emission from under the surface of the planet. So what you see in the cyclotron maser spectrum, if you look at the spectrum of the cyclotron maser, so this is intensity as a function of frequency, then you get some kind of sudden cutoff in the cyclotron maser spectrum. And you see this in Jupiter. This happens around 40 megahertz for Jupiter. Why 40 megahertz? Because the surface field of Jupiter at the surface is about 14 Gauss. And the cyclotron frequency corresponding to that is 40 megahertz. So by measuring this cutoff, you can measure the surface magnetic field of the object. And if you know the radius of the object, then you will know the magnetic moment. Yeah. I'll Okay, I'll come to that. So that's the next thing to work out is the strength of these signals. The star also has some radiation. Yeah. Yeah. So so both very useful questions for me because those are the two things I want to discuss next. So let's take the distinguishing first because that flows into the narrative quite easily. So let's work out what the properties of this emission are. The first thing is that it happens at the local cyclotron frequency. That's the first property. The second property of the emission is it is instantaneously narrow band. But of course, because you're seeing the emission coming from a huge region of the magnetosphere, it appears like it's broadband emission. But in one given location, it's very narrow band emission. Typical bandwidth is 1% or less of this kind of radiation. Okay. The next property is that because it is coherent emission, it is induced emission, it can reach extremely high brightness temperatures. So brightness temperatures of, in theory, till 10 to the 24 Kelvin are fine. So the radiation brightness temperature can be 10 to the 24 Kelvin. Whether it reaches that or not depends on conditions, how it's driven, all of that. But now we come to the most important, which is that the radiation is beamed. Why is the radiation beamed? Because right now I took a very simple case where both electrons had no parallel velocity along the magnetic field. If the electrons have a parallel velocity, then the radiation will be Doppler shifted in the rest frames, right? And the resonance condition changes slightly. So if the electrons have a parallel velocity, then the resonance condition basically looks like this. Okay. So here I've taken this to be the non-relativistic cyclotron frequency. Sorry? No, there's no beaming here. There's no beaming. This is simply Doppler shift because the electromagnetic wave has a parallel wave number, K parallel. Okay, that's the parallel wave number of the electromagnetic wave. V parallel is the parallel velocity of the electron, which is feeling the electromagnetic wave. So K parallel times V parallel that is the term which gives you a Doppler shift the electron sees in the electromagnetic wave. Omega is the wave frequency, and I've separated all of this because we have now stipulated that the electrons might have a shift in their resonance because of the Lorentz factor, right? So this will be very close to the cyclotron frequency, but not exactly. So this is the wave frequency. This is the non-relativistic cyclotron frequency. So this is if gamma were 1, this would be the electron cyclotron frequency. Okay, so that is the resonance condition. So now you see that the resonance condition describes a locus in that V parallel V perpendicular plane. Okay, and it is in that locus where you have the exponential growth of radiation. It's only the resonant electrons which will contribute. Not all electrons are resonant. Why? Because they all feel different Doppler shifts to the wave. So not all electrons can be resonant. Okay. So you can actually solve this, and I can post the notes for everyone where I show how you would solve this. These give loci in that V parallel V perpendicular plane. And then it is in that electrons in that loci which actually give the radiation. Now, because you can actually show that you can actually show that K parallel for any of these resonances is going to be very low. So the radiation actually doesn't go parallel to the magnetic field. K parallel is very low. It actually escapes perpendicular to the magnetic field. Okay. Maybe later we'll pull the screen down and I can show you the plot of what the loci look like. And you can see that you have very low K parallel to satisfy the resonance condition. Sorry? Yeah, the idea is very similar to the cyclotrons you would make. The same idea, the same resonance is used to create microwave, for example, in a device. Yeah. So you have very low K parallel in the wave, which means that the wave almost leaves perpendicular to the magnetic field. So what happens because of that is, if you have a magnetic field, let's say along the Z direction where the radiation is happening, the radiation leaves at large angles to the magnetic field and very specific angles. So the radiation leaves along the thin surface of a cone with a large opening angle with respect to the magnetic field. Okay, so if you have, so if the radiation is, let's say, happening here, it will leave at a large angle to the magnetic field and it will leave along the surface of a cone. So only observers who are in the sight line which cuts by this will see the radiation. The other observers are not going to see this radiation. Okay. So of course, if the radiation happens here, you get a cone here, which is slightly tilted with respect to the first cone. And all the radiation goes along the surface of the cone. So now imagine what happens when the planet rotates. When the planet rotates, you can have these cones come in and out of your field of view, right? So you will actually see a rotationally modulated emission, and I'll show you tomorrow examples of how you see this rotationally modulated emission. In reality, nothing is changing in the planet. It is just that because it is rotating, you get the appearance of rotational modulation comes because of the beaming of the radiation. So you see a rotationally modulated beam of radiation. And to answer your question, so the same emission can happen on a star. There's nothing to prevent a star from, giving the same kind of cyclotron emission. But if you know the rotation rate of the star from spot modulation, and you measure a rotationally modulated signal, which is not at that rotation rate, then it is conclusive that it cannot come from the star. And so you might not know which planet it is coming from in the system, but you will figure out that it is coming from something else in this system. It cannot be coming from the star. And not only that, as a bonus, you would have measured the magnetic field of the planet, and you would have measured its rotational rate, because you have seen the rotational modulation of the planet. What's more interesting is you have measured the internal rotation rate of the planet, because you're not measuring the surface rotation rate, you're measuring the rotation rate of the magnetic field. And that is generated in the dynamo layer inside the planet, right? So what you have measured is the internal rotation rate of the planet. Question? Yeah, that's a good point. So if everything is perfectly symmetric, then there is no modulation because nothing changes. Yeah. No, I'll come to that. So no. You can get cyclotron maser emission without the star also from the planet. It's just the rotation of the planet can induce that emission. So that's the next topic I want to cover. What powers this emission? Yeah. Yeah. No, I haven't imposed it in the resonance condition. The resonance condition just tells me it helps me identify which electrons contribute to the radiation. And after that, I still have to do an integral over the momentum distribution along the resonance curve, along the curve where the resonance is satisfied. And there on that curve, I must have a population inversion. Yeah. So to give you a little more flavor for what is done, that resonance condition actually is in the general case is an ellipse in this plane. Okay. So if I vary the value of K parallel and omega, I get different ellipses in the plane. Okay. So a typical ellipse might look like that. Right. So at the correct value of K parallel and omega, that ellipse will be tangent to the loss cone. And that is where the population inversion is. So when you integrate some function over this ellipse, you're going to get a positive growth rate because of the population inversion. Yeah. So it is that resonant ellipse which will contribute, which means there is a particular value of K parallel that works. All other values of K parallel will give you exponential damping. They'll not give you a positive growth rate, because I might have another ellipse which does not intersect because this is where the gradient is the highest in perpendicular momentum. So I can choose a different K parallel but then I won't get a positive growth rate. And that's why the radiation is highly beamed, because only one value of K parallel really works. Yeah. Any other questions? Super. You don't need a dipolar field for cyclotron laser to operate. You can have multipolar fields. In fact, in the sun, the only time we see cyclotron laser emission is in these really small coronal loops. So you don't really need. You just need some magnetic trap, right? So you can have a multipolar field. You just need a magnetic trap to do this, to make this work. Yeah. Okay. Okay. Are you guys finding this interesting? And you are able to follow this, I hope. So if you're not, then let me know. Or if it is too obvious what I'm telling you, then also let me know. Because then I can just go faster and cover other topics. So is this too fast or too slow? What's happening right now? It's fine. Yeah. 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 Yeah, we are in the cone of Jupiter. Yes, yeah, yeah. But if you observe the solar system from the ecliptic pole, then you'll not see Jupiter because the cone has a very wide opening angle. People who are in the ecliptic plane are differential observers in some way. Yeah, I mean, all of this can change if there is a huge dipole tilt. The magnetic tilt can be large, and everything changes, of course. Yeah. Yeah, that has a high tilt. Yeah. The the problem with Uranus is we know it's a radio emitter, but it's not studied in great detail because for the case of Earth, Uranus, and Neptune, the three of them have roughly the same strength field. It's roughly a Gauss. So all of their cyclotron cutoff frequencies, the peak frequency at which they can emit is around like a megahertz or something. And that is below our ionospheric cutoff. So we cannot see Uranus from here. We can't see our own planet cyclotron emission from here because the ionosphere prevents the 1 megahertz is below the ionospheric plasma frequency. So the waves don't reach the Earth. So Uranus and Neptune, I think if I'm correct, the first and the last time we saw that cyclotron emission was with Voyager. And then it's never known. Yeah, so we don't have like fantastic idea on. We know that they are cyclotron emission, but it's not been studied in great detail. Jupiter is the one studied in fantastic detail because this you can observe from the Earth. So. Okay, so there are two ways. So what we have learned now is, yeah, question. That's it. Yeah, that is interesting. Yes. So there are two issues with it. One is a theoretical issue. The other is a practical issue. The theoretical issue is that once the electrons become ultra-relativistic, then you get what is called synchrotron emission. So cosmic rays are ultra-relativistic. So if you take a single cosmic ray particle in a magnetic field, its spectrum is broadband. So this is, let's say, frequency. And this is the intensity of radiation at some frequency. So the radiation is extremely broadband in synchrotron emission. It becomes broadband because of the aberration of light. So even the relativistic electrons are doing cyclotron motion, but because they're highly relativistic, their emission is highly beamed. So every rotation, you just see a single pulse. It'll be linearly polarized, that's true, but then it'll be very broadband because you see a single pulse, so its Fourier transform is very broadband. And so because it's very broadband, it's hard to figure out what the resonance frequency is, the cyclotron frequency is. That's the theoretical reason. There's a practical reason, which is that the radiation is going to be, for all intents and purposes, too weak to detect. Because the cyclotron maser emission is amplified radiation, we have a hope of detecting this from exoplanets. The synchrotron emission is simply not. So the easiest way to see that would be to just work out the brightness temperature of radiation. So in the Rayleigh-Jeans regime, your brightness temperature so this is the beam solid angle of the emitter, like how big the emitter is on the sky, flux density of the emitter, ergs per second per hertz per square centimeter, Boltzmann constant, brightness temperature of the radiation, lambda is the wavelength. So you could work that out. So I can give you a rough idea of what the brightness temperatures look like in the radio band. So for a given brightness temperature, you could work out what the flux density will be. Let's call it TT for brightness temperature. And this is in Janskis. I don't know if you have heard of what a Jansky is. So one Jansky is now, to give you a sense of how sensitive telescopes are, we can see things which are the faintest things we can currently detect in the centimeter wave band is about a few microjansky. 10 microjanskys is the faintest thing we can detect. Okay, that's where the synchrotron emission would appear, somewhere in the centimeter wave band. And it has to be 10 microjanskys for us to detect it. Okay, so that is the essential problem. The brightness temperature of synchrotron emission cannot exceed 10 to the 12 Kelvin. You can show that because when it exceeds 10 to the 12 Kelvin, you get huge inverse Compton losses. So in most cases, you're going to get brightness. So if I and here, if I go to the centimeter wave band, then let's say I put 1 centimeter, and I have to reduce this again by 8 orders of magnitude, 4 orders of magnitude. Sorry. So the synchrotron emission is pretty hard to detect because of this reason. So here I've assumed something which is roughly the size of a planet. So that omega, the beam solid angle, is the size of the area of the object divided by the distance to the object. So that's where the distance comes. Yeah. So the essential problem is it's not bright enough for us to detect it. Okay. So we have now seen that you need some kind of an accelerated population of charges to create this maser. Because if the population is not accelerated, then that impact of the gyration frequency on the impact of gamma on gyration frequency will not be felt. So you can't have very cold charges. You need charges which are almost trans-relativistic, such that their gyration frequency depends on their energy through that gamma. So that's what you really need, which means that you can't just take thermal electrons and create cyclotron maser emission. It's very hard to get cyclotron maser out of just thermal plasma, which is in the magnetosphere. You need to create some kind of an accelerated population in order to get it. And so there are a few ways in which this accelerated population is created. First of all, you've seen that the magnetic field cannot do work on the charges. So it's hard for the magnetic field to accelerate the charges because it doesn't do any work on the charges. So it can't increase its energy. And so you need some other mechanism to create that acceleration. And I think that'll be the topic I want to discuss next, but I think we have run out of time. I'm right. Yeah, we could take questions and we could continue this status. Yeah. Any questions? Yeah. Yes, that's what I want to discuss next, where the rotation breaks down, and that's how you get the acceleration of that. Yeah. That's one way. The other way is magnetic reconnection with the wind of the with the solar wind. Is how you accelerate. In a pulsar, you mean? No, no. I mean, in pulsar, you have to do a fully relativistic field. So a lot of the things we said will not hold in a pulsar. The pulsar has a relativistic pair plasma in it. So yes, some things are similar. The field still cannot do work on the charge. I mean, okay, there are some things which are just electrodynamics and they're similar, but we didn't. The only place where we brought relativistic effects is we just said, well, the effective mass is gamma times m, right? And that doesn't work. You have to do a fully relativistic treatment for a pulsar. Yeah. Yeah. So you should think of the ECMI a little bit like these old rifles, where you have to load something and then you fire, and then you have to wait for it to load again, right? So it's a little bit like that. So what happens is the instability starts in some local region, and that region can just be like a 30 kilometers in size. And I'll show you some data where you can actually see individual masers, which are forming when you take data in high time frequency resolution. And so that's just like a 30 kilometer, 100-kilometer size region where you have that maser. And because the growth rates are so high, it just saturates within a millisecond. And the kinetic energy of the electrons, whatever can be liberated, is liberated. Around 1% actually of the kinetic energy of the electrons is liberated. And then you just have to wait for the instability to develop somewhere else. Yeah, so it's a little bit like load and fire, load and fire. The firing is extremely fast. The energy is liberated very quickly. But the transit time of the electrons when they bounce is a few seconds usually. So loading takes a few seconds, firing is immediate, basically. Yeah, so what happens is because the individual site is very small, the moment you integrate it, what happens is you end up not seeing the individual pulses because there are a lot of them operating at the same time. But there are some special cases where you do see individual pulses, and that has to do with if you have inertial alpha wave acceleration. Because then what you're seeing is the acceleration is happening in situ. There's alpha waves traveling along the magnetic field, and the acceleration is happening in situ. And then the release is also happening in situ. So you actually see, you can see the alpha wave moving, and then you can see the frequency increasing of the maser because it goes towards the pole. Yeah, but there are special cases. In the general case, you can't see the individual maser sites. There are too many of them overlapping already. Very similar to pulsar emission. It's very hard to see the individual spikes. Yeah. Yeah. Yeah, so the drift doesn't matter so much for the radio emission itself, but the drift is important for other things in terms of working out the dynamics in the magnetosphere and things like that. But as far as it comes to the radio emission, the curvature drift, the curvature drift is too slow in any case for it to for the rate of its for its acceleration to matter. The hierarchy of timescales is such that the cyclotron timescale is always the smallest, right? The rate at which the gyration happens. That time scale. So we did the energy hierarchy. We could do a time scale hierarchy. And in that hierarchy, in the magnetosphere, the cyclotron rate is the fastest, right? And so that is the frequency at which you will get the emission, because that's the frequency at which acceleration is happening, right? And so that for that reason, the curvature timescales are in hours, the curvature drift. So you're never really going to see the radiation from the curvature. It's only the cyclotron timescale. The next timescale is probably in the ionosphere is the collisional timescale. Can start approaching the cyclotron timescale in the denser regions of the ionosphere. And that has an important effect on the radio emission. That timescale does have an important effect because the collisions allow cross-field drift of the electrons. It allows electrons to move across the field lines, which is not possible in the magnetosphere. In the magnetosphere, they have to stay on the field lines. But in the ionosphere, the collision with neutrals will allow cross-field drift. And that creates a cross-field current. And that allows a large-scale current system to set up in the magnetosphere. So that's the next thing I want to cover, but we should break now. Yeah.